All right, welcome back. We've already laid the groundwork with series circuits and Kirchhoff's voltage law. Today, we're going to build on that with a really powerful shortcut that, trust me, you're going to use all the time, the voltage division rule.
You know the drill, right? Meticulously finding the total current, then using Ohm's law over and over for each component. But what if there was a way to just zoom in and find the voltage across one specific resistor without all that hassle? Well, there is, and it's a massive time saver.
So here's our game plan. We'll kick things off by seeing why VDR is just a faster way to get the job done. Then we'll get into what voltage division actually is. After that, we'll run through a calculation, cover the super important rules on when you can and can't use it, and then we'll wrap it all up with the key takeaways. Okay, let's jump right in. Why is this rule so essential? Well, at the end of the day, it's all about making your circuit analysis quicker and more efficient.
The whole point of the voltage division rule is to let you bypass those extra steps. Instead of having to solve for the entire circuit's current just to figure out the voltage drop on one little resistor, VDR lets you calculate it directly. It's just a clean, elegant shortcut.
So what's actually going on in the circuit that lets us take this shortcut? Well, it all boils down to a really fundamental principle of how series circuits behave.
Okay, so the formal definition says the supply voltage gets divided up among all the resistors in that series loop. Think of it like they're all sharing the voltage. But the key here is how they share it. It's not an equal split unless all the resistors are identical. The division is proportional.
And honestly, this principle is super intuitive. A resistor with a higher resistance value is going to hog a larger portion of the total voltage. And a smaller resistor, well, it gets a smaller share. You can almost think of it like each resistor demands its proportional slice of the voltage pie.
All right, so now let's see how we can turn this idea into a simple, really powerful formula and actually apply it to a circuit.
And here it is. The voltage across our resistor of interest, let's call it V1, is equal to the total supply voltage, V, multiplied by a ratio. And that ratio is just the resistance of our target resistor, R1, divided by the total resistance of the circuit, which in this case is R1 plus R2.
Let's work through a quick example. We've got a 12-volt supply hooked up to two resistors in series. R1 is 2 ohms and R2 is 4 ohms. Our mission is simple. Find the voltage drop across R1. So, following the formula, we just plug in the numbers. That gives us 12 volts multiplied by the ratio of 2 ohms over the total of 2 plus 4 ohms. We simplify that denominator and we get 12 times 2 over 6. And 2 over 6, that's just 1/3, or about 0.333. And that quick calculation gives us our answer. The voltage drop across R1 is exactly 4 volts. See? Super quick, super clean, and we never had to calculate the circuit's total current. Now, let's do a quick sanity check here. We just found that the 2 ohm resistor gets a 4-volt drop. So what about R2? It has double the resistance at 4 ohms. Is its voltage drop going to be higher or lower? Well, based on that proportionality principle, it has to be higher, right? And it is. It'll be exactly 8 volts. And look at that. 4 volts plus 8 volts adds up to our 12-volt supply, which means Kirchhoff's law holds true. Perfect.
Now, as powerful as this tool is, it is absolutely crucial to know its limits. So let's cover the really critical rules for when, and more importantly, when not to use VDR. So when is this the perfect tool for the job? VDR is your go-to for any pure series circuit when you just need a fast voltage calculation. It's incredibly useful in design too, like when you're creating a specific voltage reference or in signal conditioning, where you need to scale a voltage down precisely. And this right here is the most important warning I can give you. This simple formula we've been using is exclusively for pure series circuits. The second you introduce any components in parallel, the rule, as we've written it, completely falls apart. You can see the difference so clearly here. On the left, a valid circuit, just a simple series loop where VDR works perfectly. But on the right, someone's added another resistor in parallel with R2. That single parallel branch changes the entire game. It alters the equivalent resistance, so that simple R1 plus R2 in our denominator is no longer correct. You absolutely cannot use the basic formula here.
All right, let's bring this all home and do a quick recap of the most important things you need to remember. So here are the essentials. VDR is your shortcut for finding voltage in series circuits. It's built on the idea that voltage divides in proportion to resistance. Higher resistance gets a higher voltage drop. You've got the formula, and most importantly, you have to remember that critical limitation. It only works for pure series circuits.
So mastering voltage division for series circuits is a huge step, but it probably leads you to the next logical question. What happens in a parallel circuit? It's not the voltage that divides, it's the current. So how do we handle that? Well, that is the perfect topic for our next explainer on the current division rule.